Okay, so in this video, I'm going to be talking about question 1 from the spring 2020 midterm. The first thing we do is we just load in the brains data set. So now the 1A is asking us to do a train test validation split. So that's pretty standard. So what we do is we get all the indexes of this brain data set. So just 1 through 96, and we do sample of that. So what it does is it gives us a permutation of those indices from 1 to 96. Technically, what it does is it samples without replacement the same number of elements as there are in the vector 1 through n row brains, which just means in practice a permutation, right? So gonna look something like this. So I'll just make sure that I'll set the seed to 0 before I do that so that the results are consistent. And what it's going to look like is, so this is this. So train IDX is indices from 1 to about the index at like the location that corresponds to 70%. So 70% of the indices rather in 1 through n row brains are over here. So here there is like a little bit of a thing where we need to pay attention. So we need to say we already included this one. So for valid IDX, we'll start with this one plus 1. And that's going to be up to 85%. So pretty standard. So at that point, we have our data frames. So brains valid and so on. So let's look at brains.test. Looks like this. Okay, so you have whatever 14 of the mammals are here. So now the question is also asking, why do we want every one of those data frames to be large? And there is a subtlety there. The reasons are different for the training versus validation versus the test. So we'll start with the training. Why do you want a large training set? Well, because basically, as a general rule, the more data you have, the less there is overfitting, and the more the predictor that you learn is going to be generalizable in the sense that it's going to work on new data as well as the training set, just because the larger the training set, the more representative it is of the data in general. Okay, so improve generalization, avoid overfitting is the answer. We want accurate predictions on new data. So why do you want a large test set? It's different, right? So the test set is not used to make the predictor. It's just used to evaluate the predictor. So basically the problem is that if the test set is too small, then just by chance, the correct classification rate, or in this case, the routine squared error, or whatever you use in order to evaluate the model that you learned, it might be very good or it might be very bad just by chance if the test set is very small, right? So the larger the test set, the more accurate you'll get the estimate for how well you'll do on new data. Again, because the test set would be more representative of the data in general if it's larger. If it's small, it might not be representative. But that's a different reason. It's kind of getting the best predictor that you can versus getting an accurate idea of how well this predictor is going to work on new data. So I'll say accurate here, actually both precise and accurate. There's like arguments for using each word, but I'll go with accurate. So what about the validation set? So it's kind of in the middle. So the validation set, you don't really use it in order to fit the model, fit the predictor, but you are kind of using it in order to determine the configuration of the predictor that you're using, or to choose between different variants of the predictor. And if your validation set is small, well, it might be that you'll choose the predictor that works well on that validation set, but if the validation set is not representative of the data in general, then the predictor is not going to work as well as it does on the validation set on new data on average. So the larger the validation set in that sense, the better, the less of a chance you have of getting an unrepresentative validation set on which you select the model that does well on that, but the model might not do well on genuinely new data. Okay, so it's kind of similar to the reason that you want a training set that's large. Now, with the test set specifically, I would say there is a limit, right? So if you have like 2 million samples in the test set, you don't really need more. Now, it's true that technically, if you have a larger test set, you'll get like more accurate, a more accurate assessment of how well you'll do on new data, assuming that the test set is exactly representative of new data. But usually there is some bias in terms of how you get the test set, which means that that's more of a concern for a large enough test set, the bias, than that 2 million is like not large enough. So unlike with the training set, where I would say always the larger the better, with the test set, there is a limit. Above a certain limit, it doesn't really matter if your test set is larger. So that is 1A. So 1B asks us to use graphs in order to start building the model that predicts the weight of the brain. So I'll just kind of do some scatter plots here, right? So, and I'll draw kind of straight lines because I'm going to be using linear regression, right? So this does not seem that awesome. So really the pattern seems to be more like this than it's like a linear pattern. So that suggests that a log transformation might be appropriate. So I'll try to transform the x-axis. And that's maybe slightly better, but actually if you transform both the x and the y-axis, that becomes very clearly very nicely linear. So probably what we would conclude is that if we are to use the body weight in order to predict the brain weight, we should take the log of both the body weight and the brain weight. So we can also look at the litter size. You were not required to do all of that, just kind of a little bit to demonstrate that you know how to do it. So here we're trying a log-log plot with litter and brain, and this is kind of like roughly linear. So you can just try to take the log of the brain weight, not the litter, and you could argue either way about which is better. So here we are trying it without any transformations. That's clearly not good. So definitely log brain. How to transform the litter and whether to transform the litter, unclear. So we'll leave it with this. And in 1C, what we'll do is we'll do our usual thing where we fit the model in a training set and we evaluate it using the validation set. And then finally, we'll select the model that works the best. So this is similar to what you did for project 1, for example. So here I'll define my little RMSE function. So because I'm predicting log brain, what I'll do is I'll predict and then I'll take the x. So that's going to be the brain weight. And now I'm going to be computing the root mean squared error where I got my prediction for the brain, not the log brain, because I'm taking x of this. Okay. So I'll try just predicting brain using body with a training set and evaluate it in the validation set. I got 375. So here log litter helps me a little bit. I'll also try log gestation. So that seems to be helping. So that's smaller. Smaller is better. So I'll try to do both log litter and litter. People sometimes do that. It's fine to include both the log litter and the litter. You did not have to do it exactly like this, of course. You should just have demonstrated the process a little bit. So here we have 273, which is a little bit better. So we'll go with this. And like you could try other variants as well, of course. So we now need to evaluate it on the test set. And what we get is 431. As you see, quite a bit larger than what you see on the validation set. But that's what you get sometimes. And so here, like what's 431? So we're going to say that on average, we expect to be off by no more than So this would be 860. This is just twice the RMSE grams. Okay, so that's the interpretation for the RMSE. So that was question 1.